Problem 1, tightly packed balls in a box. Oh, I gave that title there. So each edge of a cubical box has length 1 meter. The box contains 9 spherical balls with the same radius r, and the center of one ball is at the center of the cube, and it touches the other 8 balls. Each of the other 8 balls touch 3 sides of the box. Yeah, so thus the balls are tightly packed in the box as in the figure below. So each one of these ones touch this line or this side and this top one and the other side there. For example, this one here. So each one touches 3 and so on. So there's basically tightly packed 9 tightly packed balls right here with one in the center. Like that. And the box is 1 meter. Each side is 1 meter. And the question is asked: find r. So in other words, what's the radius of this ball? So every one of these balls with the exact same radius, and so on. So what is r if you have 9 packed like that inside? Alright, so let's take a look at the solution. Actually, before we get to the solution, we're actually given a hint from our calculus book. So hint says, if you have trouble with this problem, read about the problem-solving strategy called use analogy. And I'll put a here like that. Read about this problem-solving one. And this is actually from an earlier video or an earlier chapter, but I didn't actually make a video specifically on it, but I'm just going to read what the that section of the calculus book said. So use analogy. Try to think of an analogous problem that is a similar problem, a related problem, but one that is easier than the original problem. If you can solve the simpler problem, then it might give you the clues you need to solve the original, more difficult problem. For instance, if a problem involves very large numbers, you could first try a similar problem with smaller numbers. Or in our case, this one's going to be helpful. If the problem involves 3-dimensional geometry, you could look for a similar problem in 2-dimensional geometry. Or if the problem starts with a general one, you could first try a special case. So in our case, we're going to use we'll look at a 2-dimensional problem first. So here it is. This one's 3D. It's all complex. Well, we'll look at a two-dimensional, basically analogous case. So solution: solving the 2D case first. So since 3-dimensional situations are often difficult to visualize and work with, let us first try to find an analogous problem in 2 dimensions. And the analog of a cube is a square, and the analog of a sphere is a circle. Thus, a similar problem in 2 dimensions is the following. And this one is, it states, if 5 circles with the same radius r are contained in a square of side 1 meter, so that the circles touch each other, and 4 of the circles touch 2 sides of the square, find r. In other words, we're just going to have, imagine you just have a 2D version like this. So you'll have one in the center, and then one like here. This one touches 2 sides, one and right here and there, and this one, and they all touch each other. I'm just drawing it really bad. This one goes like this, and I think it goes like that. No, actually, it is right. These all touch the sides and each other, but not these ones do not touch. So there's a difference there, and this goes like this, etc. So again, very analogous to the 3D case right here. So again, there's a separation from here. The center one does in between here doesn't touch here, but they all touch at the spot over there. All right, so that's how it looks like there. All right, and here I quickly just pause the video and just fix this. I just drew these out better, just using just built-in shape creator thingy in OneNote. All right, so that's how it looks like, and yeah, these all touch the sides again. Close enough. All right, so going further, so to solve this, we need to solve for r. So basically, we want to solve for r like that, for example. All right, so I'm gonna leave it like that. So the diagonal of the square can be determined by the Pythagorean theorem. So we know the sides are 1, so we could solve it out. So we know that the sides of the overall square is 1, 1, 1, 1. So we can go Pythagorean theorem right here and solve C, and recall that C is just, well, C squared equals to A squared plus B squared. In other words, we're going to get C is equal to plus or minus, and we just take the plus. I always do plus or minus just because inside could be negative as well. It's a very interesting concept. Anyway, so the sides are 1. 1 squared plus 1 squared equals 2. Well, square root 1 plus 1 is 2. Like that. So the diagonal is square root 2. So we're going to need this for our finding our r. Alright, so now going further, so let's write the diagonal of a square as a function of r and x, where x is the diagonal of is the diagonal square. No, I mean where x is the diagonal of a smaller square of side r, and solve for r. Yeah, so in other words, we have something like this. I just copied it from the solutions manual. Yeah, basically you have these three. If you look at a diagonal, so you have the radius here, r, 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 r. So there's 4 r's, but now we're going to have this square. So let's say we draw it on this side as well. So we'll have x side like here. These are x. X is the diagonal. So this is radius r, r, and then there's x is the diagonal like that. So then the diagonal of the overall diagonal, this equals to square root 2, which we had written over here. Square root 2, this is going to equal to, well, 4r plus 2x. And we know x is a diagonal where the sides are r, so we can just use Pythagorean Theorem as well. So then this is all going to be, let's put these all together. Basically, we're going to get I'll put it separately. So x is equal to, well, again, plus or minus, we'll take the plus, square root, and then it's going to be r squared plus r squared, which equals 2. This is going to be just square root 2, and then, square root 2 r squared, which equals to square root 2 r, like that. Yeah, so that is the x value there. So I'll box this, and we're going to throw that inside. What we're going to end up having is, the overall square root 2 is equal to 4r plus square root 2r. Alright, so that's if we factor out the r and move it on this side, is r going to be, well, 4 plus square root 2 equals to square root 2. So put this all together, r is equal to square root 2, you guys divide it out, 4 plus square root 2. So there is our r value. Alright, so now that we've solved the 3D case, the 2D case, so now we could solve the 3D case. So this one, let's use these ideas to solve the original 3-dimensional problem. So the first thing that we need to do is find a diagonal. So the diagonal of the cube can be determined using the distance formula in 3D. So again, from my earlier video right here. So the distance formula we have, so the distance P1, P2 between the points, P1 and P2 in 3D is equal to basically the same thing as the Pythagorean Theorem, but it's in 3D now. So the difference of these coordinates, then squared, and then so on. So x, then we'll have the x1 squared, the y's, and the z squared on all square root. And in our case, what I'm going to do is I'm going to just draw the cube. Say we have a cube like this. So this is our cube. Here, and we'll just do coordinates quickly. So let's say this is the z axis there, and it goes like this all the way to the origin. So let's say the origin's there. What I'm going to do is go all the way across here. This is the x, and then this is the y. It goes across there, and we're going to go point from this part all the way over to here. So all the way from there to there, this is the origin is 0, 0, 0. So again, in our case, the x1s all just vanish as 0. So 0, 0. And then this part right here, in our case, all the sides are 1. So 1, 1, 1. So then this right here is going to be 1, 1, 1. So in other words, our diagonal, I'll just put d. So this right here, d is equal to square root. Again, it's just going to be 1 squared. So 1 minus 0, squared 1 plus, 1 minus 0 is 1. So for every single 1, 1 squared plus 1 squared plus 1 squared equals to square root 3. So that is our diagonal. Instead of square root 2, we have square root 3, which is quite interesting. Alright, so similarly, let's write the diagonal of a cube as a function of r and x, where x is the diagonal of a smaller cube. Again, instead of a square, we're doing a cube with edge r, and then we're going to solve for r. So in our case, here, let's just draw our cube in 3D, like that. So there's our cube. So draw it a bit better. So this is our cube like that, make it a bit better. Okay, so there is our cube, something like this. And this goes like that, and line up these together. So there's our cube. Alright, so that's the cube, and I'm going to draw in red our balls, or spheres, small spheres like that. So I'm going to draw it, it's a bit hard to, well, we just need 3 of them. I'm going to go diagonal from this corner all the way to this right here. So we're going to have, I'm going to draw a big one like that, and another one like that, and then one all the way like this. Okay, so we have like that. I'll make it try to make them all the same size. Alright, so I have drawn them like this, so that's good enough. And now what we're going to do is I'm going to draw in blue our distances. So from here to here, this is our R. We also have another R like that. Then we also have another one here. So we have R, 3 R's, and there's also one here. That's also our R. So we have 4 R's, again, same thing as before. Yeah, but now we're going to have a cube here. So we're thinking this in 3D. This is the diagonal of a smaller cube with sides R. So we're going to go from this point like that. Then we're going to draw it like this. Then down. This lines up like that. And this goes across like that. So just think of it as a cube there. And here I just fixed that up. So again, all the sides are going to be R. R, it's all the same radius there, R everywhere. And then now we have a diagonal, it goes across this to there, and that's going to be our X. And I'll draw that actually a different color so it's more visible there. We'll go this one in green. Alright, so green is going to go across to there, and that's our X. Alright, so that's our X. So now we could just get back into the same exact, we're going to have exactly the same formula. So the full diagonal, so I'll call it D. This equals to cube root 3. This equals to, this equals to 4. Yeah, it's going to be 1, 2, 3, 4. And there's also another point like here. This is going to be also X, like that, X. So it's going to be equals to 4R. So 1, 2, 3, 4, and then plus 2X. 2X. And where again, X is just the diagonal, this equals to square root, and then this is going to be in 3D now, R squared plus R squared. It's a diagonal of the cube instead of a square, like that. So we're going to have square root 3 now, and then R like that. So that is our X. Alright, so if we put this all together, we need more room, we'll move it over here. So D equals to square root 3, and then equals to 4R plus 2X, which equals 2, and this is going to be 4R plus the 2X is going to become, well, again, it's square root, it's going to be 2 times square root 3, and then R, square root 3R. Alright, so that's what we have there. Now we can just factor out the R. So we're going to have, and move it over to here. So R is going to be 4 plus 2 square root 3. And this equals to square root 3 like that. So this means that R is equal to square root 3 over 4 plus 2 square root 3. Alright, so we could stick with this right here, but my calculus book actually continues further and simplifies it further by multiplying it. I believe it's called the conjugate. So the bottom right here, instead of so multiply the top and bottom by this denominator, but with a negative. So we'll have some bunch of canceling out stuff. So 4 minus 2 square root 3 like that. So it's basically the idea is just only have 1 square root as opposed to 2, and also make it on the top as opposed to the bottom. So this equals 2. This is going to be 4 square root 3. Minus 2 times square root 3, this is just going to be 3. Over, so 4 times 4, so just FOIL it out, 4 times 4 is 16. So this is going to be, I'll just keep it as squared. 4 times 4 is 4 squared, and then 4 times 2, it's going to be 8 square root 3. And now multiply this by, this one here is going to be positive 8 square root 3, and then the last one, multiply these together, is going to be 4, and then 3 times, square root 3 times square root 3 is just going to be 3, like that. So then extend this out, this cancels, and we're going to be left with, this is 16 minus 12, this equals 2, and this part right here is just going to be 4 square root 3 minus 6 And this is going to be, this is going to be 16 minus 12 equals to 4. So 4 square root 3 minus 6 over 4. And divide this out by 2. And we're going to get this is going to be a 2, 3, 2. And then also divide this all out. This is going to be, or you could go, I'll put it up afterwards. So square root 3, or 2 square root 3. And then minus, all those do 2 squared 3 over 2. And then you can also, again, simplify it even further. And this equals, divided out, it's going to be square root 3 minus 3 over 2. Alright, so that is our radius. So again, you can simplify it. These are the exact same thing. Square root 3 over 4 plus 2 times square root 3. Or simplified to square root 3 minus 3 over 2. Amazing stuff. And this is in meters, so I'll put a bracket like that, and I'll put meters like that. So, meters.